Hey everybody, Mr. Johnston here, and we're going to talk a little bit about this idea of resonance. This is in your textbook, it's section 9.7, so you can look there for more information. So first I want to start with a quick definition of resonance. So resonance is when two or more valid Lewis structures can be drawn for the same compound. And so a lot of times when we're talking about resonance, really what we're thinking about is this idea that electrons are moving between positions. Let me show you what I mean by this. So let's consider the chemical ozone. So ozone has a formula O3, and if I count it up, it would have 18 valence electrons. I know that each oxygen has 6 valence electrons, so in this formula, if there's 3 oxygens, 3 times 6 is 18 valence electrons. If I were to draw out a Lewis structure for ozone, what I would draw is something like this, where the oxygen in the middle is double bonded to the oxygen on the right, and then a single bond to the oxygen on the left. If I count up, and then there's these lone pair electrons, so I want a quick count, see how many electrons I have, and then check to see if everything has an octet. So 2, 4, 6, 8, remember a dash represents a pair of electrons, 10, 12, 14, 16, 18. So there's my 18 valence electrons. And if I want to see, does everything have an octet? So this oxygen is surrounded by 2, 4, 6, 8 electrons. This oxygen in the middle is surrounded by 2, 4, 6, 8 electrons. And this oxygen here on the left is also surrounded by 2, 4, 6, 8 electrons. So each atom of oxygen has an octet. Now, that oxygen, or this ozone, could be drawn a different way. I could also draw this ozone with the double bond between the first and second oxygen. So this double bond now in the different position. Everything still has an octet. There's still 18 valence electrons. So what we have are two different Lewis structures for the same compound. Now, the reality is that the compound doesn't take one or the other shape. Instead, this pair of electrons, this double bond, it resonates or moves from one position to the other. And along with that pair of electrons, the other pairs of electrons here also resonate and move around. And so what the reality is it's actually more of a hybrid, where a resonance structure, the way that we represent it is we draw the 3 oxygen atoms, and we draw the double bond as the second bond is a dotted line to represent as delocalized, or those moving electrons. Also, you'll notice that in my resonance hybrid drawing, I left off the lone pair electrons. So this type drawing is called a resonance structure. And there's multiple resonance structures for this compound ozone. And what we end up doing is making a resonance hybrid. Let me show you another quick example besides this one with ozone. So my next example, let's take a look at the polyatomic ion nitrate. So nitrate is NO3. It has a -1 charge. if I count up, nitrogen has 5 valence electrons plus 3 oxygens. There's 18 more valence electrons there. And then it's a charge, so there's an additional 1 electron. So that's how we get a total of 24 valence electrons. Now, if I were to draw out the Lewis structure for nitrate, I could think of a couple of different ways to draw it. Here's my first Lewis structure. So nitrogen in the center, and then a double bond to the oxygen going right, a single bond to the oxygen going up, and a single bond to the oxygen going left. And when I look at this, nitrogen in the middle has an octet. The oxygen on the left has an octet. The oxygen above has an octet. And the oxygen on the right has an octet. And I've used a total of 24 valence electrons in that drawing. Well, I could draw another resonance structure for this as well. As a matter of fact, I could draw 2 more resonance structures. So each of these are equally valid Lewis structures for the nitrate ion. I could draw the double bond on the right, I could draw the double bond up, or I could draw the double bond on the left. And so each of these is equally valid. And the reality is this double bond and these electrons, they actually do move from one position to another. So what we need to do is have a way of representing these delocalized electrons. And the way that we represent these delocalized electrons is with this resonance hybrid drawing. So again, if we kind of think about the fact that these double bond can be in more than one place, the way that we represent it is with this second dashed line that's in all of the spots where the double bond could be. Also, you'll notice that I left off the lone pair electrons. The next thing that I would like to touch on as far as Lewis structures go is this notion of isomers. In our textbook, it's section 12.6 and 21.3. Isomers are molecules with the same formula but different molecular structures. And that's important to note because if two things have different structures, then they also have different properties. We most often see isomers with organic or carbon-based molecules. It turns out that carbon is an atom that can form 4 covalent bonds, and it can result in this huge variety of different molecules. One that I would like to look at is an alcohol that's 3 carbons. And so here, let's look at this formula, C3H7OH. This is propanol or isopropyl, and we'll look at the 2 isomers of propanol or isopropyl. And so I can draw a Lewis structure for this compound with in 2 different ways. And I actually went ahead and built this molecule with some 3-dimensional models. So here, this is 3 carbons long. Each carbon has the 3 hydrogens on this one. This middle carbon's got 2 hydrogens, and then the OH is on this end carbon. Another way that we could actually build this molecule is if I put the OH group on the middle carbon. In order to do that, I'd have to actually take this thing apart. So break the bond here, and physically rearrange the molecule to put that OH part on a different carbon. So now I've made an isomer. I've made an isomer of this propanol. So this is isopropyl, whereas the one over here is propanol. And one thing that you might be kind of wondering about is there other ways to rearrange this? One way that you might think is, oh, well, what if we drew it like this, where the OH part is, instead of facing up, it's facing down. And I would say that it's actually the same molecule. If you think about this three-dimensionally, right? It's the same molecule, you just flip it over to make that OH group facing down. And the same over here, if I look at the other isomer, where this OH group is, instead of in the middle, it's on the end. In this first one, I have it drawn on the right side, and on this one, I have it drawn on the left side.